Today, we're really trying to be focused on working, but I just wanted to take a tiny bit of time here at the beginning to review a little of what we did yesterday and demonstrate doing it with Desmos because that will likely speed up your process of completing assignments. So, I did make another assignment. It's one question shorter than yesterday's because I took off the problem that was about determining if an ordered pair is a solution to a linear equation. We've done that with every assignment for a while, so I'm hoping we're getting enough practice. We already knew that anyway. So I'm going to be giving us a short quiz soon. I'm not sure yet if I'm going to put it up in the stream for tomorrow's asynchronous day and ask you to do it tomorrow, or I may delay it till Thursday. Um, we'll see by the time tomorrow gets here. But either way, it's just going to cover what we've been doing for the past week or so, making sure we can tell which ordered pair is a solution to an equation, determining which equations that we're looking at in algebraic form are um, linear equations and which ones are not linear, and determining if a set of ordered pairs represents a linear function. That's what we did yesterday, and I'm going to review a little bit here in a minute. Just going backwards in our slide deck to remind you that right here we have that slide that tells us the three things that we can look for and know if any of those three things are going on, then it's not a linear equation. So the exponents besides one, the variable in the denominator, or the variables being multiplied together. Those are the three things that we can say, oh, because that's going on, this is not a linear equation. All right. We got any questions at the moment, guys? Cool. And let's take a look at what I was just going to do is walk through a decent part of yesterday's assignment. So there it is on one side, and on the other side, this is my recommendation, which you've heard from me plenty of times. Where did it go? Is to do a split screen on your Chromebook and have your Desmos calculator in one and your um, Alex assignment in the other. So let me go back to the first problem of this assignment, which is the one that I didn't include in today's assignment. Click on my graphing calculator. But we hopefully are becoming very familiar with the fact that the way we check to see if this negative 3, 7 is a solution of this linear equation is just to replace the x with negative 3 and the y with 7, and then see if it turns out to be a true equation, which would mean the left side equals the right side. So we're trying to see, does 5, and then where the x is, I'm putting parentheses and replacing it with the number negative 3, closing those parentheses, and typing in plus 2, parentheses to replace the y with the number 7. And sure enough, it's telling me that that does calculate to be negative 1. So that's the reason that says yes. Does anybody have questions about this problem? I don't want to spend too much time on it unless you guys do have questions. All right. Then 2 and 3 are just where we're identifying is it a linear equation or not. All these were linear because they didn't have any of those three weird properties except for D. It had an exponent other than 1 shown. This would actually be what's called a quadratic equation. Anytime the highest exponent is a 2, you're actually looking at a quadratic equation. All right, so I'm not going to keep spending time on that. Let's jump to what we were doing yesterday. So what we learned yesterday is that in order to be a linear function, we have to have a constant rate of change. And the way we determine our rate of change is looking at how x changes and how y changes. So kind of like yesterday, I'm going to start out by highlighting all my x's in yellow. Just makes it really obvious which of these crazy numbers in this list are actually x values. So there they are. Those four numbers are x values. And then we just start saying, well, how do those x values change? When I went from this -3 to this -2, what was the change? Well, I happen to know, and I bet most of you do too, that that's an increase of 1. But here's how here's how Desmos can help us figure that out. If I want to know how it changed, I take the new value -2 and subtract the previous one. So that's what I'm going to do over here. -2, I have to subtract the previous value, which was a -3. So -2, take away -3. Sure enough, Desmos agrees. It's not putting the positive sign. Remember, I was just doing this plus sign to emphasize it's an increase of 1, not a decrease of 1. And then I'm going to keep going. The next one is, how did it change when I went from this -2 to this -1? I again believe that's an increase of 1. That's supposed to be a plus sign there, Mr. Reed. So if I come back over here to Desmos and do the new value, take away the original one, -1, take away -2. Just to clarify, that's the new value, take away the one right before it. Okay, it's always the one right before it. And sure enough, it's an increase of 1. And then we got one more change to look at. When I go from -1 to 0, yep, that's an increase of 1. But Desmos will let me take that 0 and subtract the previous number to prove that it's really an increase of 1. All right, we took care of all the x values. They are consistently changing by an increase of 1. That's what we had to figure out, but that doesn't mean the ordered pairs are consistently changing yet. Right now, we just know the x part is. We have to look at the y part also. So that's what I'm doing now. In green, I'll highlight all my y values. I tried leaving them unhighlighted in one of my classes today, and my brain wouldn't let go of the things that were highlighted. So I decided I'm better off highlighting both parts, just in different colors. Okay, so this y value is -4, and it goes to a -2. That's actually an increase of 2. But just in case Mr. Reed doesn't know what he's talking about, I'm going to take that new value, subtract the one right before it, and yep, Desmos agrees it was an increase of 2. Then I'm going to go from this -2 to this 0. It's also an increase of 2. And so if I go ahead and say I've got 0, my previous value was a -2 that I'm subtracting, Desmos agrees. Right now, we have every reason to say this is a linear function, except that we're not done checking all of the y values. But every x value changed by 1, and so far all the y values increased by 2. So now we're going to look at this last one, and that's where we actually do have a little problem, because I went from 0 down to -4. It's a decrease of 4. And as soon as I find that there's a y value that changed different from the way all the other y values were changing, then I know that it can't be linear. So you see, I can look at all the things I entered to make sure that I entered them correctly, but I've got all my x values changing by increasing by 1, then all my y values are doing great till I got to the last one, and it's nonlinear because of that. Any questions there, guys? Okay, I'm gonna get that out of our way, take a look at the table of values here, and I will be glad to slow down and go over this more thoroughly with anybody that would like to, but I'm going to do it quick and then create breakout rooms. Actually, I'm going to try and see if I've pre-assigned breakout rooms. We'll see if it automatically takes you there or not. That's what I was trying to experiment with, just to see if it would work. Anyway, all of my x values are here, and all my y values are here. Yesterday, I actually wrote each of these out in ordered pair form for you, but I'm not going to do that right now. But right here, when I go from a -1 to a +1, that increased by 2. Going from 1 to 3, I'm increasing by 2. And going from 3 to 5, I'm increasing by 2. So my x values are changing consistently. Over here on the y values, going from -1, I'm actually going down to -6, and that would be a decrease of 5. Here I go down to -11, which is another decrease of 5. And here I go down to -16, which is another decrease of 5. So this one, all the x values increased by 2, all the y values decreased by 5, so it's definitely linear. Okay. Any questions there? If not, here comes some breakout rooms. We'll try out this idea of, do they actually successfully put you guys in automatically. It may not work. We're about to find out. It worked on you too, huh?
It forced me to go, and I was like, well, that's a switch usually says, you know, you can go. And I was just like, oh, wow.
Well, I don't know that we'll always keep it that way, but I pre-assigned. I don't think you can do that unless you pre-assign them, but my 7th period in particular, I've got students that just don't want to bother to go to a breakout room, so I wanted to have the ability to send them.
Exactly.
So, cool. I'm glad that was successful. Now I know it does work. I assumed it would, but
yeah.
And because they're pre-assigned, they'll pretty much always, you know, if we do that consistently, they'll pretty much always be in the same rooms, and then we can kind of rotate how we approach bopping from room to room.
Nice.
Anyway.
Okay.
Right.
That's good.
It also, but I didn't pre-assign you, and I didn't pre-assign my Chromebook, and it automatically assigned them. So I'm wondering if, I don't know. I think I had tried that before without doing any sort of pre-assignment. I don't think it worked. So I might see in another class if I can not pre-assign and make them automatically go. Who knows?
Well, good for you for figuring it out. Good job.
Crazy. Hey, Miss Banks has questions. I'll go check.
Oh, okay. Well, I didn't even see. You want me to go check on her? Or are you going to go do it?
I can go check on her.
Okay.
I'll be back.
Okay.
Hello there, Chanel.
Hello, Mr. Reed.
How goes it?
I'm doing good. How are you?
Very good, thank you.
That's good to hear. I have a question about the linear.
Uh-huh.
So what makes it linear again when it comes to like the numbers?
That's when we have to see our each, as we go from one point to another, are the X values changing by the same amount each time? And then if the answer to that is yes, we have to see, are the Y values also changing by the same amount? They don't have to change by the same amount that the X values do. It's just that as you go from one point to another, do the Y values change? Here you go. Let me share my screen again, and maybe it'll make it a little more understandable. Can you see my screen at the moment?
Yes, sir.
So these were the X values as we went from this first point to the next one. This X value changed by 2. That's what the X values did each time. Y values, they each changed by going down 5 each time. So it's that fact that they're changing by the same amount. It's what we call a constant rate of change. That's why it's linear. If I go back up to that top one that we did and see if, yeah. So I highlighted the X values in yellow for that one, but each time they went up by 1. Then the Y values in green, they were going up by 2 until I got to that last one, which went down by 4. And right there, it's that fact that this Y value changed by a different amount than the rest of them that made me say it's not linear. Does that help at all? we can do another example or work on whatever problem you're on.
So that reminded me how to do it.
Okay, super. Anything else I can do for you right now?
No, sir. Thank
All
you.
right. Thanks for asking.
You're welcome.